Okay. Hello, everyone. Please sit down. Let's begin. Okay, so a quick announcement before we start with today's lecture. The project is open. You've received an email, I believe, to this regard. So there's the first task 0. That's just a quick, very quick thing to get you familiar with the protocol, with how to interact with the project server, the URL you can read here. And this is just meant to familiarize with the interface and how the submission works. That will be done in later tasks as well. So task 0 is not graded. Task 1 will be graded. Task 1 is online as well. And task 1 is about regression. Okay, and so we've already talked about this quite a bit here in the lecture. It's actually broken down into 2 parts. One part where we basically you get a chance to try out cross-validation for model selection, and the other part where I actually submit a linear model on a test set. So that's already in this protocol where you do have to submit predictions, and you're going to be evaluated based on these predictions. Okay, so that's the first main task of the project. All the instructions and details and so on will be available on the project server. Okay. Also, just another brief announcement, right? So as we mentioned, the projects will be carried out in teams of up to 3 students. In principle, you could do the project alone if you want, but of course, if there's more people in the team, that's the opportunity to share the work, right? So teams of size 1 will not be treated differently than teams of size 3, okay? And so also the other aspect to building teams is that you can change teams, right? So between the tasks, you can sign up for different teams, right? Just so that there's this flexibility. Okay, so that's the project, more per email, online, on the project server, etc. Okay, so we are currently discussing classification, right? Let's do this after the break, yeah. So, extremely important instantiation of supervised learning, right? And so in contrast to regression, where you predict a real valued output, and the classification you predict the discrete outputs, right? Yes, no, possibly more than 2 values. We've been focusing on binary classification here, and in particular, we've been discussing linear classification, which we want to continue today. Okay, and so we talked about what is a linear classifier, how do we parameterize them, just a quick reminder, because we'll be continuing to talk about this extensively today, right? So the way we're going to do it is we're going to essentially use a linear function, right? So basically W transpose X, the same kinds of functions we've been discussing all the time in the context of regression. But in the difference to regression is that we don't just take the output of that function as our prediction, but we apply the sign function to it, right? So we threshold it to get this binary prediction. Okay, so the types of hypotheses, the types of functions that we want to fit, essentially have this form, right? That take an input X, a d-dimensional feature vector, they multiply it with a set of weights, right? And a product of our weight vector W with this feature vector X that gives a real number. And now we're going to look at that sign, right? And that's the output of this hypothesis, okay? And so the level set of this, right, they're hyperplanes. In particular, the level set of 0 of this function is the decision boundary, which is shown here, right? So it's a linear decision boundary, okay? So these are linear classifiers. This is the class of hypotheses we'll be considering. And the question is, how do we find them? And what we had talked about is that, so we started with basically the objective of trying to find a linear classifier that makes few mistakes. And this led us to consider this optimization problem here, where we basically search over all of these hypotheses, hence all of these weight vectors W, for the one that minimizes the number of mistakes, which is the one that minimizes the 0-1 loss. Right? So that is our first objective, right? Seems like a reasonable one. You want to find the linear decision boundary, the linear classifier that classifies as many examples in the training set correctly as possible. And then what we noticed is that this resulting optimization problem, which is on this slide here, in contrast to the one that we encountered when discussing linear regression, least squares regression, is much harder, right? This is a not even continuous objective function, right? And so in general, actually trying to solve this optimization problem optimally is in fact NP hard. So what we've looked at instead is reformulations of this optimization problem using this key idea of surrogate losses, right? So we took the 0,1 loss, and which is difficult to optimize, and replaced it by a new loss function that's simpler to optimize. This led us to this first surrogate loss. We'll see many others in this course. This one here, right, which is this perceptron loss function, basically just the positive part, right, of minus y times w transpose x, is given by this maximum of 0 and minus y times w transpose x, right? And that has the nice computational property that it is convex, right? So it means sums of these convex functions are also convex. So the overall optimization problem actually is a convex problem, like in regression. That means we can hope to use gradient optimization techniques, right, in order to solve it. Moreover, it's aligned with the problem that we wanted to solve. In what sense? Well, it's aligned in such that the surrogate loss LP, this perceptron loss of how you refer to it, right, is 0 if and only if the 0,1 losses is 0. Okay, and we'll get back to this fact later. Okay, so that seems like a natural objective. It's computationally nicer, right, and it's still aligned sort of with the problem, right, that we want to solve. Okay, and so this led us to consider this optimization problem, right, where we want to minimize the empirical risk, the same as in least squares regression, but instead of looking at the sum of squared residuals of our model, we would now look at the sum of these perceptron loss functions evaluated on the weight vector W, the model parameters, and always taken with respect to the current data point that we're considering. Okay, and so this is an optimization problem that we can try to solve, and let's just look at this. So here's basically an illustration. Okay, so this is here a data set that we'll be looking at, right, with the positive and negative class indicated by the stars and these blue squares, respectively, a two-dimensional example data set. And what we want to do now is we want to solve this optimization problem here, right? And so what we will start with is basically this algorithm that we've discussed in the context of linear regression, namely gradient descent. So you're going to compute the gradient of this cost function, take a step in the negative gradient direction, and proceed until convergence. And what we ended up in last lecture is the expression for the gradient of this cost function, right? So we worked out what really is this gradient. I'm just going to remind you of that, right? So this is, again, our hat. So P is this empirical risk associated with this perceptron loss to sum of these individual per data point loss functions. So the gradient is just the sum of the gradients. Now the gradient for each of these little loss functions here, right, associated with one data point, is worked out down here, right? And in order to get that gradient, we did this case analysis, right? Are we in this 0 part, this constant 0 part, or are we in this slope -1 part, right? In this part where it's non-zero. And we computed the gradient in both of these cases. Obviously in 0, the gradient is just 0. In the other case, it's just minus yi times xi, right? And that means that if we compute the gradient of the overall objective, which is given here, right, with respect to these weights w, then essentially we get the sum over all of terms. Of course, we only keep the terms that are non-zero, right? The rest doesn't contribute to the sum. So effectively, the gradient at the current model parameters w is just given as the sum over all misclassified examples, right? Misclassified according to the current model of yi times xi, right? So essentially, the gradient is always pointing in the direction of the data, and so you're essentially moving a bit towards the data. And so in particular, if there's an example that we should have classified positively, but we actually did not, so the yi in this sum here is 1, right, is positive, then we move towards the direction of xi. And if yi was negative, right, so we got a false positive, right, so we wrongly concluded that xi is positive, then we move away from xi. Right? That's basically the interpretation of the gradient. Okay, so let's see a little demo of that algorithm, and then we'll discuss some other algorithms related to this problem. Okay, and so let me do this here. And so basically, this was our data set, and let me just run the gradient descent algorithm. And so here's what it does. Okay? So it converged after a relatively small number of iterations. And now it doesn't move anymore. Why is that? Well, the gradients are exactly 0. There's no point that's misclassified anymore, so the gradient is exactly 0. Okay? Yes?
Stop evolving as soon as there was no misclassifications, correct?
So we never shift our data points. We shift the weight vector, right?
No, we're saying if the separation between the data sets
between
the two classes have been more pronounced.
Yes. Yes.
The gradients would be 0
Yeah.
as soon as you
Absolutely. Absolutely. So absolutely. So keep that thought, and we'll get back to it in a couple slides. Okay? So good. Yes.
Why is it not a straight line?
Why is it not? Oh, yeah. So this is just an artifact of plotting. Sorry. So this is the PyPlot's approximation of a straight line. The way we plot it here. Okay, it's our fault here. So, okay. It's supposed to be a line, right? Just imagine this is a line. It's just the resolution of the. Okay. Good. So this is basically gradient descent. Now I want to talk about a different algorithm. And so this is essentially what's now most widely used for supervised machine learning problems. And so the idea is the following. So we talked about gradient descent, right? Where basically, in order to compute the gradient direction, you look at all possible data points, right? You sum really over all data points. Here it happens that some of them don't show up because you classified them correctly, but it's a sum essentially over all the data points. Okay? Now, this is fine if you have a small data set, right? If your data set consists of a few thousands or 10,000s of points or so, maybe this is not a problem, right? If you talk about really large data sets, like millions of examples or tens or hundreds of millions of examples, then this is not typically a good idea. So why is that? Well, it's obviously expensive, right? You're investing a lot of effort to evaluate that gradient exactly. And the important thing is that, of course, the gradient, we will use it in order to sort of move towards the direction of the optimum. But if you're very far away from that optimum, right, the gradient direction might not really be very informative, right? We sort of just want to get a good direction to make progress, right? We don't necessarily care about having a completely correct gradient. That's sort of the idea, right? So that's the potential to gain some computational advantage by not computing the full gradient, right? So we might save computation by not computing the gradient exactly, but still hopefully get convergence by somehow identifying a good direction to make progress toward. Okay? And so that's the idea behind algorithms like stochastic gradient descent. And here the idea is to basically get stochastic estimates of the gradient. Okay, and so it works as follows. So what you're going to do is you're basically taking our gradient. So if you think about our gradient of this empirical risk, right? That's 1 over n. So what we can do is we can use the linearity of differentiation, right? So this is what we've always been doing, right? To push the gradient inside the sum, right? So we have the loss associated with the ith example, right? And so now what we can do is we can observe that this is basically an average, right, of the gradients of all the data points that we have. Okay, but an average, we can always interpret as an expectation, okay? So you can basically just think about this here as an expectation of the index I drawn from the uniform distribution on 1 all the way up to n, of the gradient of the loss of W with respect only to this randomly chosen data point. Okay? So this is just the same way of writing this, right? So this is the definition. If you spell the definition of this expectation, right, we get this expression right. Okay? So you can interpret basically the cost function, right, the empirical risk, already as an expectation, right, of the true gradient. Okay? And so now what you can do is we can try to approximate this expectation using fewer samples. Okay? So you can try to basically approximate this cost function, not by an average of essentially all the points in our data set, but a subset of them drawn somehow uniformly at random. Okay? So we can basically approximate this by a sum, right, of I1 up to IM drawn from this uniform distribution on the whole data set of the something from J now from 1 up to M of the gradients taken only at those points that we've picked. Xi sub j and yi sub j. So that's the idea. Okay? And so by the law of large numbers, Sm keeps growing as we pick more and more points that we draw. This estimate is going to converge, right, to the true gradient of the empirical risk that we might want to optimize. Okay? So that's basically the idea. And now that gives, right, rise to an algorithm called stochastic gradient descent, which you actually get here even just by this special case of picking one single example. So SGD, stochastic gradient descent, is basically this algorithm here with m equals 1. Okay? So it means you approximate this gradient of the entire data set by just looking at the gradient of one single example. Right? So here's the algorithm. So we basically start with some initial guess. We would iterate. And then every round, we're going to pick a data point, x prime, y prime, from our data set, uniformly at random, with replacement. Right? You would typically, in the end, run over a number of iterations that might be bigger than the number of examples. Right? So this is done with replacement. And then you essentially apply the same update rule that you would do for gradient descent. But now you only look at the gradient of the loss of this one single data point. Okay? So basically, this is what this does here, right? So you take the previous weight vector and you subtract eta t, the learning rate, times the gradient only with respect to the loss, right? Evaluated at this one random point, x prime, y prime, that you've picked. Okay? And now this algorithm, right, is no longer deterministic, right? Gradient descent previously was a deterministic algorithm, right? If you fix the starting point, it would always make the same set of decisions. Here, this now is a randomized algorithm, right? It would do a random walk, right? It sort of randomly walks around parameter space. But it's guaranteed to converge under some conditions, right? And now this depends very much on the problem and the conditions, and we won't be able to discuss all of them here. So what you're discussing here is the convex setting, right? We've discussed in least squares problems. There are some mild assumptions on the loss function satisfied by the kinds that we're discussing here, where this algorithm is actually guaranteed to converge to the globally optimal solution as long as this learning rate satisfies these conditions here. These are called Robbins-Monroe conditions. And those appear very often if you talk about stochastic optimization. So stochastic gradient descent is an example of stochastic optimization. And so basically what these require of the learning rate is that if you sum over t, eta t, then that resulting series has to diverge. But if you sum the squared learning rates, so sum over t, gamma t squared, it has to converge. Okay? And this sort of is is a rate of growth that basically is enough to help prove convergence under these settings. So what is the meaning here? So basically, the first one ensures that you don't get stuck after only a finite number of steps. So if the sum over these gamma t's would converge, you might not be able to move between arbitrary 2 points in the parameter space. That's sort of the intuition of why you need this divergence. But the intuition of why you need the sum of the eta t squareds to converge is that you don't have too much variance that you'll actually be able to converge in the end. Okay? So these are the Robbins, Monroe, conditions. Okay, and so one example, what's an example of eta t that satisfies this? Well, something like 1 over t, right? So e.g., eta t is 1 over t, right? Satisfies these conditions. Sum over t of 1 over t diverges, but sum over t 1 over t squared, that series converges, right? Or something like what's sometimes done is eta t is, say, okay, let me just move these examples here. Right? Another example might be something like the min of some constant C1 and some constant C2 over T, right? That might lead to schedules that sort of look like this. Right? You initially have constant step size and then you would decrease later on. Okay? So there's various different choices. Also lots of ways of adapting these learning rates in a data-dependent or data-independent manner. So there's a huge literature around this. Lots of heuristics, lots of choices that actually have guarantees under various circumstances, etc. Far too much to discuss here in this course. Okay, so learning rates are extremely important to get right for these algorithms to converge. So these are sufficient conditions to, at least in theory, get convergence. Okay, and so let's take a look at, so what does this, what does this concretely mean for the perceptron algorithm, right, just to spell it out, right? So as we had said, the gradient of the perceptron loss at some point xy, right, was 0 if correctly classified, right? So basically if y is the sign of W transpose x, and minus yx if incorrect. Right? So that means the algorithm essentially just iterates. Right? So you would start initialize somehow, right? Right? So e.g. set it to 0, right? Or some other number, right? Maybe you've already trained it on some data and you will use this as initial guess or something, right? And then basically you pick IT drawn from the uniform distribution on 1 through n. And then basically you check if YIT is the sign of, is correctly classified. Or it's different, sorry, this is YIT is incorrectly classified, right? Say W1 here. Transpose XIT. Then we would set eta t plus 1 to be eta t minus this learning rate times, sorry, plus YIT XIT. Otherwise, we just keep it. Okay? And of course, you can simulate that algorithm, right, by only drawing from misclassified examples, right? That will basically go through the same sequence of steps, right? But technically, this is the implementation of SGD. Yes?
I have a question regarding the previous slide. Completely always have the finite arrays, so I'm not really sure what's the, like, your array can go however you want in the beginning. If it continues later as 1 over t, then it will satisfy the condition.
What do you mean?
Combinationally, you have always finite number of steps.
Of course, you only have finitely many steps, right? You still want to make sure that you don't, right? I mean, so it's a long discussion about what are the right learning rates, right? But typically, you would want to set the algorithm, right, that at least asymptotically you do converge, right? And so you keep letting the algorithm run until the error is small enough, right? So, and these sort of conditions allow you to achieve this. Okay, so let's just take a quick look of how this looks like. So basically, sorry, so this is here. Okay, so what we can do is we can just set the batch size to 1 and run the algorithm, right? And this is basically what it does, right? So it jumps through the points, and whenever it encounters one that's incorrectly classified, it would do an update. Right? So let's actually reduce this a little bit, run for a few more iterations. Okay, so here it is, right? And so basically, whenever it encounters a data point that's incorrectly classified, it updates, right? And certainly needs a lot more iterations than gradient descent, right? But of course, it only sees one single data point per iteration. Okay, so that's an idea of what SGD, stochastic gradient descent, does. Now, what is done typically is you wouldn't actually just use one single data point, but you actually would set m to something slightly larger than 1, right? Pick a mini batch of examples, just multiple examples in order to get a lower variance estimate of the gradient, right? So here basically what we had discussed, so instead of setting m equals 1, right, mini batch stochastic gradient descent would be basically the same algorithm, but you pick more than 1 point, right? So essentially instead of drawing one example at random, you would draw, say, m examples at random, and then use that in order to compute the estimate of the gradients. Right, and we can just see what's the effect of this. Right, so if you pick 10 examples, right, then the gradient directions are more informative, right? Of course, the work per iteration is more informative. Okay, so that's basically mini-batch stochastic gradient descent, which is sort of the standard default choice that's extremely widely used. So one nice aspect is that since you the gradient estimate is just the sum of the gradients that you compute per points, you can actually compute the gradients in parallel across points in a batch, right? And oftentimes, of course, for very small problems, very small models, that doesn't matter. But for very large models, like neural networks with many, many parameters, it's actually very useful to be able to compute multiple gradients in parallel. Okay, so that's the idea. So this is basically just an extension where instead of looking at one single data point, you look at multiple data points, right? That you would use in order to get a better, lower variance estimate of the gradient, right? A more informative direction. Okay. Now also, of course, SGD, right? You wouldn't just apply it for the perceptron, right? You can apply it to any problem, right? Where you basically have cost functions that decompose additively, right? Or in fact, for any problem where you can basically get unbiased estimates of the gradient. Okay. And so if you think back to linear regression, right? The cost function looked the same, right? You also had a sum that decomposed additively across the data point, right? And so, of course, we could just go ahead and apply the same reasoning for least squares regression, right? Instead of computing full gradients, right? We could pick individual points, right? Or small mini batches of data points and use them in order to get the stochastic gradient estimate. I just want to show you how this looks. Right, so this is our linear regression example. Right, this is, okay, just run this. So this is basically, oops. So this here is basically stochastic gradient descent in order to fit this least squares problem. And here you see this random walk in the parameter space, right? So this is W0, W1, right? The two coefficients for the bias and slope of that line, right? That we had, right? And the algorithm was just basically computing unbiased estimates of the gradient, right? By computing a gradient not with respect to all data points, but only with respect to one single sample drawn. And you see sort of this zigzaggy random walk behavior, right? That gradient descent does. And of course, you can also pick mini batches here, right? And let's just do this to see what is the effect, right? How it reduces variance, right? So now here it always picks multiple points that are illustrated by these crosses here, right? And those together give you a more informative gradient direction. Okay? So that's basically the idea, right? So this algorithm is really extremely widely useful, right? Certainly applicable to all situations, right? Or in principle applicable to all sorts of situations where you have cost functions of this form, right? Where you essentially have a cost that decomposes additively across these data points, right? And you've seen two examples. There's many, many more. Yes. I don't know who's first. So.
Usually when we use the gradient descent and regression,
yeah.
we stop when the difference wasn't.
Sure. Okay.
Can the difference here be like, I don't know, because of the sampling, the difference is not that big? So
yeah, absolutely. So we haven't said yet about when to stop, right? So the algorithm wasn't really fully specified yet, right? So let's talk a little bit about this, right? So here, when does this end here, right? Exactly. So now one issue is, so in the convex setting, if you do gradient descent with suitably chosen learning rates, you can use as a stopping criterion basically the difference in function values between two subsequent samples. If that's small enough, you can terminate, right? So essentially, if there's too little improvement in terms of function value, you can stop, right? Or you can look at the magnitude of the gradients, right, and derive termination conditions from that, right? If the slope, and again, gradient descent tries to set the gradient to 0, right? And now, if the gradient is almost 0, then you can stop, right? These are typically stopping conditions that you would use when doing gradient descent. Okay? Now, how do you do that with stochastic gradient descent, right? Where you have only one single data point. So certainly just looking at the gradient magnitude of that random sample is not a good idea, right? So we've seen in the perceptron, for example, right? The gradient contribution of 1 point is 0 if you have it correct, and it's non-zero if it's not, right? So basically, if you were to just look at whether the current gradient is 0 or not, then obviously it would just terminate as soon as you happen to randomly have guessed one example correctly, right? So that doesn't make sense. Okay, so now what is done? What one can do? So one thing, of course, is at any given point t, right? You could try to compute the cost function, right? You could try to compute the perceptron cost function, right? And then apply a similar rationale, right? To say that once the cost function does not change much between subsequent iterations, right? The entire cost function, R hat of p, right? The empirical risk, the sum over all points, right? Once that doesn't change anymore, you could stop. But of course, that defeats the whole purpose of the gradient descent algorithm, right? Because then once you do this, you have to look at all the examples, okay? So now what that means that in practice, you would try to get an estimate of the function value itself, right? So you could, for example, look at only a subsample of points, right? And check termination against those, right? Or only after a certain number of iterations, you would compute the exact cost function and look at the difference. What you actually do, and so what's typically done is you would actually even use your training set to evaluate, to look first, decide on the stopping condition, but you might actually set aside a validation set of points that you would check for termination, okay? And so there's sort of a lot of different techniques that are done. These are some of the ideas that are used, and we'll get back to that sometime later in the course as well. Okay, so there's various ways, right? So for now, one possibility you could think about is just every so and so many iterations, say every n iterations when you made a pass through the entire data set, right? You just compute the whole cost function, right? At this point, you've anyway spent linear effort to go through all the points. Now, you might as well just compute the cost function by summing over all the points, right? And then compare essentially the cost after two subsequent epochs, right? That's sort of one concrete way of doing it that you could think about. Okay, so that's basically this. I also want to briefly mention, so we discussed, again, learning rates are a very subtle issue, right? Often it's very important to get them right for these algorithms to converge. And there's a lot of work on sort of trying to come up with good recommendations of how to pick these learning rates, right? And a lot of them actually data dependent, right? So they depend on, say, the gradient magnitude. There are some techniques of choosing even different learning rates per feature dimension. So you might not use the same step size per feature dimension, but actually adapt it per dimension. And so here are some of the algorithms, right, that are being used. Sorry, this is meant there's a D missing here, right? ADAGRAD or ADAM or RMS prop and so on are examples of adaptive learning rates that are used. Some of these do have guarantees, at least in the convex setting. But of course, it's a very large literature, and we won't be able to discuss all of this here. Okay, so just before the break, let's talk about one thing. So in particular, we've said, right, that we started off with this problem of trying to find a classifier that makes few mistakes, right? And that was this difficult optimization problem, right? The 0-1 loss. So we replaced it with the surrogate. Okay? And now we sort of made this intuitive argument, right? Saying that basically the surrogate is 0 if and only if we don't make a mistake and so on, right? And so the question is, can we say something about the performance of actually running this perceptron algorithm, right? So basically solving this perceptron optimization problem, and what kind of guarantees one can give about that resulting solution, okay? And so one kind of result that one can easily show based on this property of the surrogate loss that we've discussed, right, is basically that if the data is in fact linearly separable, so there does exist a hyperplane that makes no mistakes, then the perceptron is actually going to find it. Okay, and so I just want to go through this argument. We briefly mentioned it already, right? But I just want to spell it out here. Okay? So basically the idea, right, is so let me just give the proof sketch. Hand-waving over a few issues here. So basically, we've designed this surrogate loss, this perceptron loss, L sub p of w in the context of point xy. This is 0 if and only if so y is equal to sine of w transpose x, right? So it's actually, so there's no mistake. Okay? So what does this also mean as a consequence? Then if you look at r hat sub p, right, the actual cost function we care about in the perceptron, the sum or the average of this perceptron loss functions, right? Then this is 0 if and only basically the model makes no mistakes. Right? Obviously, right? So because it's a positive function, right? And it's exactly 0 if and only if that particular classifier is correct, right? And now, of course, by assumption, there exists some W tilde that linearly separates the data, right? So looks like this, right? So that's the exists one, right? It makes no mistakes, right? So it means that r hat of p of W tilde is 0, right? And now, since gradient descent or stochastic gradient descent, right, on this convex objective, our p hat actually converges to an optimal solution, it actually must find such a linear separator. So it converges to a minimizer it must hold that W hat in fact linearly separates the data. Okay, so that's sort of a sanity check, right? That's a result of the fact that we have the surrogate, right, which actually ensures this kind of property. Okay, now how doesn't this contradict this NP hardness of this optimization problem that we had talked about earlier? You might wonder, right? And so, of course, here we've assumed that the data is in fact linearly separable, right? We haven't said anything about what happens if it's not. Of course, in practice, most often the data is not exactly linearly separable, right? And then you can't use this argument, right, to relate the value of the minimizer of this perceptron problem, right, to the best agnostic classifier, right? So it doesn't contradict this hardness result. Okay? Doesn't mean that this doesn't generally give decent solutions for this classification problem, right? But of course, it doesn't get around this hardness of this problem. Okay? Good. So let's take the break now, and then we'll talk more about linear classification, but beyond the perceptron. Okay. Good. So back to linear classification. So we talked about the perceptron and sketched its analysis, right? And so what I want to do now is to talk about another linear classification technique that's extremely widely used, and that's very related to the perceptron. And here's the motivation, which basically comes back to a question that was mentioned before. And so let's look at this data set here, right? This two-class binary classification data set, right? And let's look at 3 candidate linear separators, right? Shown here in green, red, and black. If you just look at the perceptron cost function, right, r hat sub p, right, the empirical risk associated with the perceptron loss, can you tell which one of these solutions the perceptron will prefer? Exactly, right? So it doesn't matter, right? So the value of the cost function is going to be the same, right? So that's basically the argument we had on the previous slide, right? So r hat sub p of w is 0 for all 3 solutions, right? Because all of them linearly separate the data, right? And because of the property that the perceptron loss is 0 if and only if we make no mistakes, right? The cost function is 0. Okay? Now, which one of these solutions might you prefer? Not the perceptron, right? So, do you have any preference among them? Once again, the green one. Okay, and so why? Any reason?
Because it's like if you try to put some linear, there is an equidistance between the first features and the minus features from the side.
Right, so it's sort of far away from both classes, right? So equally, same distance away, right? It's equidistant to both classes, okay? Right, so and why is this a good thing? Well, there can be multiple arguments of why this might be a good thing, right? So one reason is the following. So suppose our measurements are actually noisy, right? These feature vectors, x1 up to xd, they're acquired through some noisy measurement process, right? So we might actually not know their precise values, right? So this data point here might as well be somewhere here, right? Somewhere close by if you have some small measurement errors, right? And maybe this point here, right, might be somewhere around here. Okay, this point might be somewhere around here, right? So if you have some small perturbations in the axis, right, then we might not actually see, would have gotten that exact same data set, but maybe a slightly perturbed one. Okay, now for this point, it doesn't matter. Its classification wouldn't change under any of these decision rules. But for this one here, right, it would be classified as negative, right, by the black one. And this one here would be classified as negative by the red one, right? So some small perturbations will actually lead to a different solution, right? So it's not robust against small perturbations. That's sort of one argument, okay? The other argument is, and we've been drawing from some distribution, right? So we assume that our data set is actually drawn from some distribution. We only get to see some finite samples. And say, suppose there's some sort of Gaussian distribution, right, that is spread around those points here, right? And so maybe that's sort of the standard deviation of these points, right? Sort of the level sets of sort of one standard deviation away from the mean, right? Then basically, you might as well expect to see many more points somewhere within these ellipses, right? Somewhere close to the data somehow, right? You just haven't sampled them yet because you have too few observations, right? And the green one here in the middle, right, because it's far away, right, it would still get it right, versus the red and blue solution would make mistakes. Okay, that's sort of the high-level heuristic motivations why you might prefer the green one. Okay, and so the technical term for being as far away as possible from both classes is called margin. Okay, so basically the property of this green hyperplane here is that it's the linear classifier that has the largest margin. Okay, and just to formally, or to explain what is the margin, here's the picture. So basically, this is the, suppose we consider this candidate decision boundary in blue here. Okay, now what these dashed lines, sort of the red and the green dashed lines are, these are basically decision boundaries that are parallel to the blue one and then same distance away from the blue one and pushed as far as possible until they touch the examples from both classes. Okay? So that's basically what this picture illustrates. And the margin is this distance here. Okay, so the distance between any of them, right? So these are the same, right? Same distance. Okay, and that's called the margin gamma of the resulting classifier. Okay? And so now, just looking at the number of mistakes doesn't say anything about the margin, right? That's something purely based on the training data, right? So it's basically here, this is, right? So these three objectives, these three different solutions here have the same number of mistakes, right? But their resulting margins would be very different, right? So this point is very close to this one, right? And to the black, and so this data point is very close to the red type of thing. Okay, so they have very small margin. Whereas the green one has very large margin. Okay, and so the linear decision boundary that has the largest margin is the decision boundary that we seek to identify when solving for the support vector machine optimization problem. Yes. Yeah. So we haven't said anything yet about what happens if it's not linearly separable, right? And so the question is, what does it mean if it's not? And I'm actually not going to discuss this in too much detail here. Okay, so that's sort of the intuition. So basically what you want to do is you want to not just find a linear separator, but you want to find one that is far away from both classes, equally far away from both classes. Okay, so that's large margin classification. And now it turns out that this can actually be achieved, we can modify slightly the preferences expressed by our loss functions so that we actually find this large margin solution. Okay, and so here's basically how it goes. So this is the 0-1 loss, right? So again, this is this plot that we've seen now many times. So y times w transpose x is right, the same term that we had looked at in the perceptron loss. So it's positive if it's correct, negative if it's incorrect. And this red line here is the 0-1 loss, right? It's 0 starting from 0 in the positive part, and it's 1 if you make a mistake, right, if it's negative. Okay? And so this black line here, this is the perceptron loss function, the surrogate that we have been discussing. Okay? And now the issue with this perceptron loss, right, is that it doesn't express this preference, right, of not just getting the classification right, but also having some distance, right, to misclassifying example. And turns out we can encourage this by using a slightly different loss function. Okay, slightly different loss function. So what we can do is we can use this loss function. Okay, so this looks almost like the perceptron loss. It's just shifted. Okay, so the formal definition is given down here. So loss function evaluated at our model W at point x and y is the max of 0. That's the same as we had in the perceptron. But now we have, basically, we add a +1, right? We shift the positive part here up 1, right? So essentially, we look at the max of 0 and 1 minus y times w transpose x. So what does this mean? Well, in order to get 0 loss, you not just have to classify correctly, right? But you actually have to classify correctly by some margin, by some distance. Okay, so this is what this new loss function here encourages, right? So it's not enough to merely get it right, but you want to get it right by some minimum amount, right? A minimum amount of 1. Okay, so that's what this cost function here decides. Now, there's another nice interpretation of this. So except for sort of encouraging some distance, right, of the data points from the decision boundary, right, that's what's captured here. This is also an actual upper bound on the 0-1 loss, right? So this green line here, this green loss, is an upper bound on this red 0-1 loss function, right? So what does this mean? Well, if you think about this empirical risk associated with this new loss function, it's called the hinge loss, then it, in fact, upper bounds the number of mistakes on our training data. Okay, so that's a particular numerical interpretation of it. Right, so upper bounds, so hinge loss. This is what we said here, right? So it's an upper bound on the 0-1 loss, right? So hence the sum of the hinge losses bounds the number of mistakes. It's still convex, right? It's just shifted a little bit, right? So hopefully for optimization, it's still nice. But it has this additional property that it somehow encourages some distance of the decision boundary and the data points. Okay, so this is called the hinge loss. So we also write L sub H here, right? H for hinge loss to refer to it. Okay, and then basically if you just contrast, so there's one more thing I want to point out here, and that's the 1, right? So why exactly a 1 here? Right? We said we want to maximize the margin, right? To be as far away as possible, right, from the examples. And now we just say we want to be 1 unit away. Okay? And so now this is actually a matter of normalization. And so basically, if we think about the following, right? So if you just fix some other number than 1 here, say you fix 10, for distance 10, then you would get the same solution by just scaling W by a factor of 10. All right? So in principle, what is here doesn't really matter so much, right? So what it matters is that it encourages not just getting correct classification, but getting correct classification up to some margin, right? But then, of course, in turn, we have to make sure that we care about the weights too, right? Because basically what we can do otherwise is if we have a solution, right, that only has sort of distance epsilon, right, it's a little bit positive, right, we can scale up epsilon, scale up W, and make this bigger than 1. Okay? So it means that it's not just enough to add this 1 here, right, to encourage this distance, but at the same time, we also have to try to keep the weight small now. Okay? And this yields this optimization problem here. And that's the linear support vector machine optimization problem. Okay? So this was the perceptron problem that we had before. Sorry. Xi. Okay? So, right, so this was just the sum of these perceptron loss functions evaluated at these points, right? So we replaced L sub P here, right, with this hinge loss. So the difference is in blue, right? It's this 1 that we added, right? We shifted this line. And then we tried to keep the size of this weight vector small. Okay? So that's the same kind of regularization that you've seen before, right? In the context of least squares, right? Of regression. Okay? So basically, use the same penalty term, right? To encourage small weights that we would use in least squares regression. Okay, so these are the only 2 differences, right? So essentially the support vector machine is basically the perceptron. The only difference, the small difference in terms of the loss, which in currents is sort of being far away from the boundary, and this regularization. Okay, so this is basically summarized here. So that's a very widely used, very effective linear classifier. It's basically like the perceptron, with the only difference that we have the slightly shifted loss, this hinge loss, and we regularize the weights. Okay, and so now this optimization problem here, you solve that. You basically, in the case of linearly separable data, you actually do find this maximum margin solution. So I'm not going to prove this here in this class. It's take a little while to formally derive why this is the case, but it's actually the case. So solving this optimization problem in the linearly separable case is going to find you this max margin solution. Okay, and otherwise, basically, this is just, again, of the same form, right? You have sums of terms that you want to optimize. And we can use gradient-based algorithms like we've been discussing, right? Now, there's a lot more to say about large margin classification, not just for binary classification, but also for structure prediction problems, for many other problems. There's a lot to say about these resulting optimization problems, etc. And these details are discussed in the fall advanced machine learning lecture. So there, this is going to be discussed in a lot more detail. So I just wanted to discuss the basic optimization problem. And let's just briefly talk about how do you use these gradient-based algorithms, right? Stochastic gradient descent, etc. So one thing I wanted to point out, so we discussed, okay. So what we wanted to do, right, is let's do let's try to work out gradient descent for the SVM, right? So we have now, so the problem that we want to optimize is we want to find W hat, right, in the argmin of sum over I equals, let's put 1 over n here, max of 0, comma 1 minus yi W transpose xi plus lambda times the size of 2 norm squared, right? This is an optimization problem. Okay, and now when we discussed, okay, so think about this as follows. So when we discussed the perceptron algorithm, right, we've basically talked about the gradient only of this term here, right? Of course, there's the 1. We didn't really talk about this regularization parameter, right? So we had one basic assumption that we had used, right, when deriving this unbiased estimate of our gradients is that the objective function actually decomposed as a sum of data points, right? And here, it's not just the sum over data points, but you also have this regularization term. Okay, I just want to briefly talk about how to deal with this, right? Of course, this here is equivalent. This cost function here is just the same as 1 over n times the sum over I equals 1 through n of this loss contribution here, right? W transpose xi plus n times lambda 2 norm squared, right? So I can just pull it into the sum and compensate by just multiplying by n, right? And so now we basically have a bunch of, you can think of this here kind of as a new loss function, right? That we incorporated this regularizer, right? The new function, let me just write whatever, g I of w, right? That now not just contains the loss, but also contains a little bit of the regularizer. Okay? And so now, of course, the gradient of the overall objective, let's call this here g of w, is 1 over n times the sum of the gradient of these little gi of w, right? And now we can try to get sampling-based estimates of these gradients, right? So as soon as we can compute gradients of these little gi's, we can apply stochastic gradient descent, right? So the only thing we need to do is we need to work out what is the gradient of this gi, right? So gradient right? So what is this? Well, first of all, this is the gradient of the loss. Plus the gradient of the regularizer. Right? And this here, this is basically, I mean, almost the same that we had worked out, right, for the perceptron. The only difference is that we not just check whether we got it right, but we check if we got it right by some margin, right? So this is 0 if yi w transpose xi is greater than 1, and otherwise it's basically just minus yi xi for the same, right? So same duration as for the perceptron loss. So the only difference is this here, right? We don't compare against 0, but we compare against 1, right? We want to get it right by some distance, by some amount. Okay, and then of course the gradient of this here is just what we had. So there's the n missing, right? So there's n times lambda here, right? So this is just 2n lambda w, right? For the reasons that we had worked out earlier. Okay, so this is the gradient of these gi. Okay? And now we can apply the stochastic gradient descent algorithm, right? We say would draw one example I, right? One index, one data point from our data set. evaluate this gradient, and then move a little bit in the negative gradient direction. Any questions?
Why are you deliberately avoiding the linear function support minus yxi, minus yiwt xi as a loss function? The loss function has to be non-negative for sure. Can we not avoid the algorithm for doing some positives?
What do you mean?
I mean, because you can only use the loss function, which is just
Yeah.
a line like this.
Yeah.
Why do you have to do this maximum 0?
Aha, so just the line.
Yes.
I mean, the problem is you still want somehow the cost function to be aligned, right, with the overall optimization problem, right? So it's unclear what the properties of that loss function would be, right? You can try to work it out, and actually it doesn't yield a useful algorithm for classification if you just were to take the loss function. But we can talk about it later. Okay? Okay, so one of the reasons, for example, you can make it minus infinity, right? So it's unbounded negatives. You'd have to compensate for that somehow, right? And we can talk more later. Yes?
You pull the regularization term into the sum,
Yeah.
but you multiply it by n.
Aha, sorry, that's the average. Yes, actually, we multiplied, so we don't need the m here. Good point.
Yeah.
Okay, so this should be correct. Good, thanks. Okay, fine. Okay, so that's basically the algorithm. Let me just run it. This is it here. So that's SVM. I can run it with batch size 1. And so this is just sort of the same as for the perceptron, right? But now you would not use run it for some more iterations. Right? It now not just affects the decision boundary once you are once you misclassify a point, right? But also once you're not too far away. And we can also increase the batch size, say batch size to 10. Okay. Or do full. Gradient descent. Okay. Need to check what exactly happened. Okay. Anyways, so basically that's the algorithm, right? It might, okay, I have to check what happens with the lambda here. But anyways, so, and of course, one question here is the same as for ridge regression, right? This looks like the ridge regression problem, right? And you have to choose this, this term lambda here, right? And this regularization parameter. And the question is, how do we do it? And so whenever we have to choose the regularization parameter somehow, how are we going to do it? Cross-validation, right? So we need to work more on that, right? So choose regularization parameter, cross-validation, okay? So basically, that's the same task, right? The same problem, right? That you now have to essentially balance the size of the coefficients and the goodness of fit, right? And now, one important difference that I want to just point out here and be clear about is, so in regression, right, our performance metric that we care about, the mean squared error, right, the sum of squared residuals, was exactly the cost function that we actually tried to optimize, right? The optimization problem was really aligned, right, was exactly the same as what we care about in terms of the solution that we get in the end, right? And now here, it's slightly different, right? Because we might care about the number of mistakes, but we actually optimize something else, right? We optimize the hinge loss or perceptron loss, etc., right? And so now, what you would do when applying cross-validation, right, is use the loss function, the surrogate loss, say the hinge loss, for example, in order to fit the model. But then in cross-validation, when comparing different models, you would use the actual metric that you care about, right? So you would use the, say, accuracy, right, or a number of mistakes in order to estimate the model, right? So in the training set, you fit, say, the SVM, right, or the perceptron, whatever, right, on the training folds, and then on the validation folds, you actually calculate the number of mistakes, right? You actually calculate the 0-1 loss, right? That's easy to do because you don't have to optimize it, right? It's just a number that you compute. Okay, so that's a slight subtle difference that I just wanted to point out. Okay, so, and of course, there's tools that just implement this, right? So I just wanted to discuss some of the basic algorithmic ideas here in this course, right? But there's great implementations of both gradient-based methods, right, and second-order methods, etc., for fitting support vector machines and related problems available. So again, as a useful toolkit, right, I mentioned this before, that you might want to use in the course project, right? You can look into scikit-learn, right? Here's sort of how you would do it in that Python package, right? You just instantiate a linear support vector classifier object. You choose the regularization constant. So here, this is the lambda. It's called C, right? That's the only parameter you need to give it here. You feed it the training set, right, in terms of x and y pairs, and call the fit method. And then once you've fitted it, you just use the predict method in order to get predictions on some test examples. Okay, so all of this is super easy to do. So this is basically about linear classification, both with the perceptron and the SVM. We'll talk about yet another linear classifier later on in the course. But basically, of course, the same rationale that we had talked about for regression applies to classification, right? So even though we use linear hypotheses that are linear in the parameters, we can use them in order to fit quite nonlinear functions, right? There's this example of the polynomials. By applying this nonlinear feature transform on the data, right, we can do linear regression in this transformed space, so we actually get a nonlinear model in the original space, right? And of course, that same idea works just as well for classification, right? Just because we talk about linear classification doesn't mean we talk about linear decision boundaries, right? And that's basically the same rationale. So what you might do is you might have your original instances, right? You non-linearly transform them, for example, by computing these monomial features, right? Polynomial features that we had discussed before, right? To map them into a high-dimensional space, right? So here, this is an illustration mapping from 1D to 3D, right? So basically mapping a point x to the vector 1, x and x squared, right? And now suddenly this problem that's non-linearly separable in 1D becomes linearly separable in 2D, right? Because you mapped it to this parabola, you can fit this hyperplane, even a homogeneous one that goes to the origin, and will linearly separate the data, right? And the same here, right? Of course, instead of mapping the lines, right, to 2D or 3D, right, you can do the same with the plane, right, and so on, right? So by looking at features that right, so interactions between the different coordinates, looking at these monomial features. Okay, and so one example are these polynomial features. Of course, there's many other examples that you might consider. Here's another picture of this, right? So you might have this two-dimensional data set here, right, x1, x2, right, that you might map into this three-dimensional data set here, right, a sort of a representation using all monomials of, say, degree 2, right? So x1 squared, x1, x2, don't worry about the square root 2, we'll get back to that later, x2 squared, right? And the data becomes linearly separable after you do this transformation, right? You take this two-dimensional problem where it's non-linearly separable, you non-linearly transform it into in this case, a three-dimensional data set where it does become linearly separable. Okay, and we'll talk a lot more about these things in subsequent lectures, right? And so far, it's been a bit mysterious about where do these features come from, right? And we'll discuss a lot more about how do you systematically select them, but later on, how do you reason about large classes of features without having to do too much hand designing, and even how do you learn good features from data in later lectures in this course. But just to summarize what we have here, so we've discussed the perceptron as sort of the most basic, most classical one of the most classical algorithms for linear classification. And so what's typically referred to as the perceptron algorithm is basically applying stochastic gradient descent on the perceptron loss function, right? So there's the separation between the objective and the algorithm you use in order to optimize it. We talked about sort of you can use mini batches to reduce variance. We introduced this important idea of these surrogates, right? That you have an objective that you care about, like the number of mistakes, but you actually optimize something else, right? And still make progress with respect to what you care about, right? And so we saw this in the context of the perceptron. We talked about its basic analysis, or at least sketched it. And of course, these ideas are a lot more generally applicable, right? So I'm really trying to convey some of the most important ideas here, right? So these gradient-based optimization techniques or stochastic gradient-based algorithms are extremely widely used, right? These are standard algorithms used widely in industry, not just for these types of problems, but far beyond. So besides the perceptron, we talked about the basic idea behind the support vector machine, right? That's a small modification of the perceptron, but designed in a way that it encourages margin, right? Encourages robustness. Okay, so it's the only difference is that it has a slightly different loss function, and that it basically makes use of regularization the same way that ridge regression does. So here's a little picture that I want to start building today, and we'll keep building this in later lectures of this course. And so we started talking about least squares regression, right? That was the first supervised learning problem. And now what we did is we sort of looked at polynomials, right? Saw you want to sort of keep weight small to control complexity, right? And we introduced this idea of regularization, right? And that led us from least squares regression to ridge regression. Okay, now what we then did is we started to go away from regression to classification. And the essentially only difference really is that we changed the loss function. Right? So instead of using the squared loss, right, we use the perceptron loss. Right? And that led us to the perceptron and to the SVM, right, which we again from the perceptron, but just slightly changing the loss and adding this regularizer, right? So, or in other words, you can sort of view the linear SVM sort of related to ridge regression, but we have a different loss function, right? They use the same regularizer. Okay? So this is sort of some basic recap of linear classification and regression that we've discussed, and we'll keep building and adding to this in later lectures. Another thing I want to just bring up, and we'll keep adding to this, is so an important summary. When you talk about machine learning in general, supervised learning in particular, it's important to really cleanly separate out these different kinds of concepts that you're discussing. So one is, what kind of functions or what kind of hypotheses are you reasoning about, right? And so here, we've been primarily talking about linear hypotheses, right? Certainly all linear in the weight, but of course, this doesn't mean these are necessarily linear hypotheses in the data, right? So you can still fit nonlinear functions like polynomials, etc., right, using these linear methods. So in the end, we essentially look at classes of hypotheses, right, that are determined by these types of features that we use, right? So you have to separate out what kind of functions do we reason about, right? So that's the representation, features, etc. Then the question is sort of how do we express preferences? So among all these models we can fit in this way, how do we specify which one of them we want? It means we have to typically specify some form of loss, right, that measures goodness of fit, right? We talked about classification and regression, and some notion of complexity, capacity control, regularization, right? And so here concretely we had talked about the square loss, 0-1 loss, perceptron loss, hinge loss, and so on, right? And we talked about L2 regularization primarily so far as regularization. Okay, and then the next thing, once we specified not just the function class and which of these functions we want, we have to specify how do we find them, right? How do we actually solve this resulting optimization problem, right? So typically that's some form of optimization, not necessarily, but what we focus on here. And right, for linear regression, you can find these closed-form solutions. Otherwise, we've primarily talked about these gradient-based techniques. But of course, there's other algorithms too, right, that are not necessarily based on gradient-based optimization. Then what we also talked a bit about today is there might be this distinction between what you actually optimize and what you care about in the end, right? So what's the evaluation metric, right? So for regression, we started off that being the same as what we optimized, right? We might care about the mean squared prediction error, which is the sum of squared residuals. And that's what we actually were able to optimize. For classification, these are different, right? So what we optimize is different from what we actually care about in the end, right? So the evaluation metric might be different from the loss that we actually optimize. And lastly, of course, once we have an evaluation metric, right, we have lots of degrees of freedom for all these choices above, right? Which features to use, which loss functions to use, which optimization algorithm to use, and so on, right? And we need to be able to choose between the resulting models that we somehow fit, right? And that leads to these validation questions, right? And we've discussed cross-validation as sort of the primary thing. And now, right, these are sort of 5 different dimensions that are really important. And so, of course, all of them have lots of different choices. And we'll explore many more in later lectures in this course, but I just want to explicitly lay them out because now at least you've seen some examples in them, okay? So that's basically it for today, and we'll continue tomorrow.